In 2017, 8 researchers at Google published a paper with a simple title: Attention is all you need. That paper changed everything. ChatGPT, GPT-4, DALL-E, Claude, Gemini, Midjourney. Every single breakthrough AI you've used in the past 3 years is built on one architecture from that paper: the transformer. It's not an exaggeration to say this is the most important AI architecture ever invented. It killed RNNs. It killed LSTMs. It unified language, vision, and even protein folding. And in the next 8 minutes, I'll show you exactly how it works, from the core mathematics to the full architecture, with visualizations that make it crystal clear. No hand-waving. No, it just learns patterns. The actual mechanism. Let's build a transformer from scratch. Before transformers, we had recurrent neural networks. RNNs process text word by word in sequence. Read word 1, update state. Read word 2, update state. Like reading a book one letter at a time without looking back. The problem? Parallelization. GPUs are designed to do millions of calculations simultaneously, but RNNs force you to wait. You can't process word 10 until you've processed words 1 through 9. Massively inefficient. Worse, the vanishing gradient problem. By the time you're at word 100, the network has forgotten word 1. Long-range dependencies? Impossible. LSTMs tried to fix this with gates and cell states. Better, but still sequential. Still slow. Still limited. Then transformers said, what if we process all words simultaneously? What if we let every word directly attend to every other word, regardless of distance? No sequences. Pure parallelism. Infinite context. That's the revolution. Transformers don't read sequentially. They see the entire input at once and decide what's important through attention. The heart of the transformer is self-attention. This is the most important concept to understand. Let's build it step by step. Imagine the sentence. The animal didn't cross the street because it was too tired. What does it refer to? The animal or the street? Obviously the animal. Streets don't get tired. But how does the model figure this out? Self-attention lets each word ask, which other words in this sentence are relevant to understanding me? Here's the math. For each word, we create 3 vectors: query, key, and value. The query is what the word is looking for. Think. I'm the word IT. What am I referring to? The key is what each word offers. Think. I'm the word animal. Here's what I represent. The value is the actual information to pass forward. Now we compute attention scores. Take the query of it and dot product it with the key of every other word. High score means relevant. Low score means ignore. For it, the query key dot product with animal is high. With street, it's low. With tired, it's medium. Then we apply Softmax to convert scores into probabilities. These probabilities weight the values. So it gets 80% of the information from animal, 15% from tired, 5% from everything else. That's self-attention. Every word simultaneously attends to every other word based on learned relevance. No sequences. Pure information flow. Self-attention is powerful, but we can make it even better. Multi-head attention. The idea is simple. Instead of one attention mechanism, use multiple in parallel. Why? Because different heads can learn different types of relationships. One head might focus on syntax, which words are grammatically related. Another might focus on semantics, which words have similar meanings. A third might capture long-range dependencies. In GPT-3, there are 96 attention heads per layer. Each head has its own query, key, value matrices. Each head computes attention independently. Then we concatenate all head outputs and project them back. Think of it like having multiple perspectives. One head says, it relates to animal through coreference. Another head says, tired relates to it through predication. A third captures that didn't cross is the main verb phrase. The model learns what each head should focus on through training. No hand coding. Just give it enough heads and enough data, and it figures out the optimal division of labor. This is why transformers are so powerful. They're not looking at text from one angle. They're analyzing it from dozens of angles simultaneously. Wait, there's a problem. Self-attention treats all positions equally. It doesn't know if cat is the first word or the 10th word. Word order is lost, but word order matters. Dog bites man is very different from man bites dog. Solution: positional encoding. We add position information directly to the word embeddings. The clever part? We use sinusoidal functions. For each position, we add a unique pattern of sines and cosines across the embedding dimensions. Why sinusoids? 2 reasons. First, they're deterministic. Position 50 always gets the same encoding. Second, they allow the model to learn relative positions. The encoding at position I plus k can be computed as a linear function of the encoding at position I. Look at the visualization. Each row is a position. Each column is a dimension. The pattern creates a unique fingerprint for each position. Similar positions have similar encodings. Distant positions have very different encodings. This gets added to the word embedding before attention. So now the model knows both what each word is and where it is. Problem solved. Now let's assemble the full architecture. This is where everything comes together. The transformer has 2 main parts: the encoder and the decoder. Some models use both, like the original paper. Some use only the encoder, like BERT. Some use only the decoder, like GPT. Let's trace a sentence through. Input: I love machine learning. Encoder side. First, tokenization. Split into tokens. I love machine learning, period. Second, embedding. Each token becomes a 512-dimensional vector. Third, add positional encoding. Now we know both content and position. Fourth, pass through the encoder stack. Each encoder layer has two sublayers. Multi-head self-attention, what we just learned, and feed-forward network, two linear layers with ReLU. Key detail: residual connections and layer normalization after each sublayer. This helps with training stability. The encoder stack repeats 6 times in the original paper. GPT-3 uses 96 layers. Each layer refines the representation. Decoder side. The decoder is similar but has 3 sublayers. Masked multi-head self-attention, can only look at previous words, cross-attention, attends to encoder output, and feed-forward network. Why masked attention? During text generation, the model can't cheat by looking ahead. At position 5, it can only see positions 1 to 5, not 6 to 10. Cross-attention is how the decoder uses encoder information. If you're translating I love ML to French, the decoder attends to the English encoder output while generating French words. Finally, a linear layer and Softmax to predict the next token. That's how ChatGPT generates text, one token at a time, attending to everything that came before. The entire architecture is fully differentiable. Train with backpropagation. Scale to billions of parameters. Magic. How do you train this monster? The answer is beautifully simple. Predict the next token. Take a massive text corpus, books, websites, Wikipedia, code, everything. For each sequence, the model tries to predict the next token. Compare prediction to actual. Compute loss. Backpropagate. Update 175 billion weights. But here's the insane part. Scale is all you need. GPT-2, 1.5 billion parameters. Could write coherent paragraphs. GPT-3, 175 billion parameters. Could write essays, code, and poetry. GPT-4, estimated 1.7 trillion parameters. Can reason, plan, and solve complex problems. The architecture didn't change. The training objective didn't change. What changed? Scale. More parameters. More data. More compute. And suddenly, emergent abilities. Abilities that weren't explicitly trained. Few-shot learning. Chain of thought reasoning. Code generation. This is why Transformers won. They scale perfectly. Double the parameters, double the compute, and performance predictably improves. No other architecture has this property. The scaling laws are empirical. We don't fully understand why they work, but they do. And that's driving the entire AI revolution. So that's the Transformer. 7 years after attention is all you need. It's become the universal architecture for AI. Language models, transformers, image generation, vision transformers, protein folding, AlphaFold uses them, music generation, audio transformers, video transformers. It's transformers all the way down. Why? Because self-attention is universal. It can model any relationship between any data points. Text, pixels, audio waveforms, protein sequences, doesn't matter. If there are dependencies to learn, attention can learn them. The key insights were simple. Process everything in parallel. Let every element attend to every other element. Learn what to pay attention to. Scale without limit. That's it. No recursion. No convolutions. Just attention and feed-forward layers. And it's enough to build AGI. Next time you use ChatGPT, remember, under the hood, it's doing exactly what we just covered. Queries, keys, values. Multi-head attention. Positional encoding. Layer after layer of refinement. All to predict the next token. And that simple mechanism has changed the world.